Hi there. Today we'll go over the UART or the USART peripheral. We'll go over the basics and then we'll move on to the hardware implementation, where we'll take the example of the latest STM32F401 Nucleo board. That's like kind of a development board from ST. I will just go over that just quickly, the schematics and how we can actually probe certain pins in the development boards to actually see the UART signals. Moving on. So what is today's agenda? So today's agenda would be a brief overview of the basic terminology of UART, and we'll then move over to the UART data diagram, how the data should look like, and then finally we'll go over some schematics and the hardware details. We'll just deep dive into the ST Nucleo board. Let's begin. So unlike other protocols, RS-232 is a point-to-point connection. It's not a star, not a node connection. So the output of the DTE, that is the data terminal equipment, connects to the input of the DCE or the data circuit terminal equipment. So that makes sense, diagrammatically, but the naming convention usually confuses most people. So think of TX as output. So the transmit TX is like the output and RX is as the input. That way the confusion is resolved. The key aspect to this protocol is that there's no clock between the two devices. It is completely asynchronous. That is, you can transfer data from one direction to another independently from the other direction, whether it's transmitting or not, right? So you can synchronize them, but they're not in sync using a traditional clock source, which you would do in case of an SPI or the serial peripheral interface. So and anyways, this protocol is quick and a very easy way to set up communication between your microcontroller board or your sensor. Moving on, most embedded engineers are very familiar with UART, or the universal asynchronous receiver or transmitter. So it's a microcontroller peripheral that converts incoming and outgoing bytes of data into a serial bit stream. A start bit usually initiates the serial bit stream, and a stop bit, or maybe sometimes 2 bits, completes the data word. So the UART has also an option of adding a parity bit to the stream to assist in detecting if the bit error has occurred during transmission. So what you see here in the diagram, in the x-axis the time, and on the y-axis the traditional voltage. But as you can see, here you can see the voltage level varies from 0 to 3.3 because we are working with a microcontroller, and usually most of the development boards nowadays come with a maximum of 3.3, and so in that sense it's not strictly RS 232, or what is RS 232? RS is like the recommended standard. That's the full form of that. So usually RS 232, the voltage varies from like 12 volts or 15 volts. That's the voltage levels that we are talking about, and usually and it's usually plus 12 volts and then minus 12 volts. So the minus 12 volts is the negative logic, or the zero level, whereas in microcontrollers there is no negative level, because it's just ground or 3.3. So in that way, that's the basic difference between the traditional RS-232, wherein the voltage varies from plus 12 to minus 12, and the band between minus 3.3 volts or around 3 volts and plus 3 volts, so is actually the gray area. So that's where it's very immune to noise in that sense. Considering the modern microcontrollers, from 0 to 3.3, it's very much prone to noise, and it's not recommended that you run a long line, because there may be issues of corrupting the signal. So let's actually focus, because the data format is very similar. So the voltage levels might not be, but the data format is very much similar, whether be it on microcontrollers or RS-232. So let's focus on the data format for this example. Yeah, so when there is no data being sent from the TX to RX, it's left in the idle state, which is like the active high, which is usually the standard. Whenever you want to transmit any data, we bring the signal to low for a bit. So when you send the data in TTL, serial, or be it RS-232, for serial it's usually 8 bits. The first bit you transmit is the start bit, which is usually low, and which is always low. And then after the start bits, we start transmitting the rest of the bits with the same bit length. So the width of the bit is the same. So the very first bit that you transmit after your start bit is the LSB, or the least significant bit, and the last bit that you transmit, usually is the 8th bit, is actually the most significant bit. And also, for instance, so there's a term called baud rate. So that's usually associated with your serial communication. So the width of each bit is 1 over the baud rate, just FYI. And so moving on, this is the STM32F401 Nucleo Board. So there are a lot of development boards from ST Microelectronics. So this particular version is the Nucleo 64. It's very low cost compared to other. So the past, the microcontrollers eval boards were very expensive, but with scale, the production costs have come down, and hence it's available in in $10 or maybe $20 at max. And here you see is what I'm doing is you have a USB to UART. There's a USB connection over here, and UART. So there are the breakout pins. Basically, you have TX, RX, and ground. So what I'm trying to do is I'm trying to probe the TX pin of the Nucleo board, so that we are able to read whatever the data that is transmitted from the Nucleo board to the computer. So there are programs in the computer like PuTTY, PUTTY, I don't know the pronunciation, or the real term. So there are some programs where we can actually specify the baud rate of transmission and observe the UART data. So here this is the JTAG connection, which is again connected to your laptop. This actually is very useful. So you have a ST link. So that's actually the part which is used to program the microcontroller. And so that's on board itself. You don't need an external programmer to program this microcontroller. So that's very handy in that sense. So yeah, so that's the basic setup for your Nucleo board. So you can see I'm probing kind of a jumper here. So in the next slide, I will go into the schematics. So we just take the schematics of this board, which is readily available in the manufacturer's website. I'll just link that below here also. So one of those pins is actually the TX, that is the transmit pin from your Nucleo board, which I am connecting to the RX, which is the input of this USB to UART, and I'm observing the data that's coming from the Nucleo to the computer. So obviously before this you gotta have a program that actually transmits, that actually writes to the microcontroller, writing some data to the UART peripheral of your microcontroller. So moving on, so you can see here, this is the schematic of STM32F401. So you can see here the TX and the RX. So you can see the port A, so specifically PA2 and PA3. So PA2 is the TX, and it's also connected interestingly to ST-Link TX, which is the programmer part of the board. So all I needed to do was to figure out where this jumper is, which was like this one here. So you just have to put a jumper wire on this, and then you have the data coming into your computer once you specify the baud rate. So yeah, so that's about a short introduction to UART. So I'll just summarize. So it's one of the oldest and the most widely used communication hardware, and even though it's clunky and expensive in terms of the pins, and because you need TX and RX for receive and transmit, and it's a point-to-point connection, not unlike a star connection where I2C, or in some other protocols where you have star connections, you can actually minimize the number of wires to different sensors, but it's usually very easy to set up, and hence the popularity. And so the only thing that you need to set is the base frequencies, which is the baud rate between the transmitting and the receiving device. And once that's done, you're all set. And once that's done, the rates can go from 300 hertz to almost 900 kilohertz for plain UART. And okay, so there's another. So the new microcontrollers come with something called as USART or USART. So what's the basic difference between USART and UART? UART comes, which is like, we are much more familiar with UART, but USART is a bit different. So the first difference between USART and UART is the way in which serial data may be clocked, right? So UART generates its data clock internally to the microcontroller, and then synchronizes the clock with the data stream by using the start bit transition that we saw just a few slides back. And there is no incoming clock signal to synchronize, basically. But in a USART, on the other hand, can be set up to run in a synchronous mode. So in this mode, the sending peripheral will generate a clock that the receiving peripheral can recover from the data stream without knowing the baud rate ahead of time. So alternatively, there is also an option. The link will use a completely different line to carry the clock signal. So the use of the external clock allows the data rate of USART to be much higher than the standard UART, often reaching almost like 4 megahertz basically. And usually, because it's a high frequency, so usually the for high frequency you tend to use USART, and hence it consumes a little bit more power than the normal UART. UART is much more used for low power, especially battery applications, lithium-ion batteries. You tend to conserve power, and you tend to prefer UART. So mostly, even though the USART options is available on the microcontroller boards, most of the developers use the plain UART because it's power efficient. Yeah, so that just gives you a short overview of UART. Thank you for listening.